Okay, so we are recording. Share the screen. So we are now recording. Let's go to table of contents. And as you guys might see in the syllabus, there is a 10% of the grade, which is participation, right? So that's like attendance, things like that. So I did take attendance today. So make sure you sign in and then just pass it around and then return it to me. So we have at this point in the semester done a lot of inference, right? We've looked at a lot of inference, GPTs, classification, regression. So that's very practical, right? Solving problems. But then there's also like some concepts that we want to understand, more like theoretical, but also based on some code. So these are not things that you will pass it around, please. These are not necessarily things that you will do to solve a problem, okay? But it's always a good idea to understand some of these concepts. So for the next couple of weeks uh, or so, there will be a focus on just drilling down into things like loss functions, derivatives, those kinds of more internal things that we have available of how machine learning works. So today's first lecture is going to be cross entropy. Just take it. So everyone signed in, right? So today, the first one is going to be cross entropy. And we're going to drill down into it and just get a feel. Obviously, it ties in to the lecture that we did before, classification with the wine quality data set. So we were using cross entropy, right? And we know that when these loss functions, we always have like a predicted and a real, and we're comparing them, and we're using that result to minimize some error or some kind of an idea. We want to minimize some value. So the loss function that we will explore today is cross entropy. So we can go, so you can see now in this module, I remind you a lot of this information is already in chapters 2, 3, and 4 or the PDF. Make sure you are reading this content. This is the last topic from this module. I'm going to click on code here, and you can see we've covered all of these, and the last one is this Jupyter Notebook cross entropy. So I'm going to click on that, and that's what we're going to cover today. Okay, so we're going to go over this. And we're going to use Colab just to kind of run through it. Okay, so that's essentially the idea. I'm going to go back here to the table of contents. The next module is actually called cross entropy. The link is literally to the same Jupyter. It's important enough that even though it's duplicated, I wanted it to have its own thing instead of be like lost with all the other ones, and then you don't pay attention to it. Okay, this is definitely something you should pay attention to. I could ask 5 of 10 questions just on this on the exam. Okay, so pretty important that you understand. So as we know, and as you will see with NIO, the loss function is the thing that essentially tells the model what to learn. Do you guys get that? So that's essentially what the loss function is, right? So essentially there's loss functions for regression like MSE, loss functions for classification like cross entropy, and then you can create your own ad hoc loss functions like we will start to see next week. Some comparison, almost like an if. If this value is greater than, take some difference or something like that. All right, so today we're going to look at, we talked about MSE last week, if you remember, where we were trying to minimize the sum of the errors. Today we're going to try to understand how does the machine learning algorithm learn to classify? How does it learn that, it should, given an image, it's going to say cat versus dog versus bird, right? So that's the idea. So the function that we always use is called cross entropy. It comes from entropy, which is a metric, a topic in information theory. If you probably heard that information theory was invented, literally, like the whole thing, by one person, Claude Shannon. All right, so Claude Shannon is the father of the digital age, did such things as coined the bit, and helped to measure information, right? So all that really interesting thing. So cross entropy is the original term, and then there is cross entropy, which is just an extension of entropy for us to use. All right, so as I said, we click on this Jupyter here, or that link, and it opens up our Jupyter notebook, which is going to be the discussion for today. All right, so we're going to talk about cross entropy by initially talking about entropy. So entropy is a mathematical idea describing uncertainty. Do you guys see that? So this is going to be a little bit like when you've taken a statistics class and you looked at probability and all the examples had to do with flipping a coin, right? So you remember that, and there's a fair coin and a biased coin and all that. So we're going to start framing the problem just like that first. But this actually is quite straightforward, so it shouldn't be that big of a problem. So let's, first of all, develop an intuition of just entropy itself. So entropy, as I said, is a mathematical idea describing uncertainty. Given a very biased coin, so that's not a fair coin, right? A biased coin has a preference. It's unfair. So given a very biased coin with both sides having a head, the probability of getting a head is then what? 100%, because both sides of the coin are head. Do you see that? So then the question is, similarly, the chance of getting a tail is 0. There's no uncertainty, right? And that's the key to this whole thing. In both cases, we are 100% certain of the outcome, right? It's not going to be a tail. There's no way. And in fact, it's going to be a head because both sides are ahead. Therefore, the uncertainty of this is 0. And therefore, we can say that entropy is 0. So entropy being the metric that we use to measure this uncertainty. So that's the idea. When we're sure of the outcome, it's got 0 entropy. Got it? That's the idea. So now let's take a look at kind of the opposite scenario. Given a fair coin would be, no preference. With head on one side and tail on the other side, we have reached the maximum uncertainty about the outcome. Okay? So, and the entropy is the highest. It's got a 50% chance, right? It's going to be head or tails. So that's the maximum uncertainty, and therefore the entropy is the highest. Okay? The entropy formula is given by this, essentially, and we'll write some Python code. So like this is not a mysterious thing. There's going to be the use of this function for binary cases and then for, multi-class or multi-outcome cases, okay? For most of the examples initially, I will assume binary, either or, like a coin. It's either this or that. And then later, we're going to extend it to the multi-outcome scenario, okay? Which if you've started to read the notes, you already know what I'm talking about. So the formula is the sum of the probability times the logarithm of the probability. This is just the equation that Claude Shannon proposed when he discussed all these topics. So the sum is overall potential outcome. So that's why, if it was multi-class, then it would be 3 possibilities, 3 classes. In ours, if it's a binary, a coin is either heads or tails, so there's only 2 outcomes. So you just sum this over all the possibilities. And P in this case is the probability of the outcome, right? So for a fair coin, 50% heads, 50% tails. Do you guys see that? Pretty straightforward. All right, so let's start to put some code into this so that it's not too theoretical. So let's take a look at modeling this. So we're going to model the probability. We're going to create a function that does the computation for us. All right, so notice I'm going to use matplotlib for some of the plotting, and I'm going to use NumPy, essentially. We don't need PyTorch for this one. It's just mainly from scratch. All right, here I'm creating a binary function for calculating entropy, just to which demonstrates the use of this equation over here. That's essentially what I'm trying to do. So notice the function is entropy Fn. It assumes binary, so you really just need one probability. Because if I have the probability of head on a fair coin, then I know 1 minus that probability is the probability of the other side of the coin. Do you guys see that? So that's essentially how it works. So notice also that this probabilities only go between 0 and 1. So I'm not going to calculate for cases outside of from 0 and 1. So here I return 0 for those cases. Otherwise, between 0 and 1, notice it's the sum of two probabilities, this one and this one. And the values are negative. So if you notice, it's minus. So that's why it's minus, minus. So it's probability times the logarithm, and this just works better, this log of 2. So the probability times the log of 2 of p negative minus 1 minus p times the logarithm of 1 minus p. Do you guys understand? So it's just, the binary case. Okay? So that's what I'm describing here, and that's the same equation as this one over here. Notice that the p is the same both here and in the logarithm. Make a note of that because that's going to be the subtle change in cross entropy. Okay? It's going to be the subtle change in cross entropy. All right, so let's add the function now. So we've got our function established. Now the next thing that we might want to do is just plot the data, right? So we're going to plot the data just to kind of get a feel for it. And I'm giving you the data. So I'm creating a range here from -2 to 2 that is separated by a step size of 0.1. And then here I'm creating a list comprehension. So for I and xs, what do? I plot each of those values given the function that I just created up here, entropy Fn. In particular, the values that I care about are the values between 0 and 1, right? That's essentially what I care about. This range from -2 to 2 is what? Probabilities. Do you guys see that? So I'm plotting probabilities. And then I'm just going to use some matplot functions to create the plot. And there we are. So notice that essentially this captures the whole idea of how this works, right? On one side, I have entropy on the y-axis, and this is the uncertainty. And then on this axis here, on the x-axis, I have the probability of head, right? So and this is the case of a fair coin. So if the probability of head is 0, how much uncertainty do I have on a two outcome problem? I have 0 uncertainty because it's a 0 probability of head. So guess what? It's tail. Guaranteed. 0 uncertainty. Do you guys see that? And the same scenario happens over here. If the probability of a head is 1, then I have 0 uncertainty. Do you see that? Now, what changes is as the probabilities are not 0 or 1, right? But they're somewhere in between, like a 0.20 versus a 0.80, right? And so in that case, if I have 0.20 to 0.80, that might be like here. So the entropy is like 0.5. But that's not the maximum uncertainty, right? Because given that one is 0.80 and the other one is 0.20, one is more likely to occur. So I can make some predictions about it. But the maximum uncertainty happens when the probability of head in a binary problem is 0.50, because then the probability of tail is also 0.50. So I have the highest entropy. Do you guys understand? That's the whole idea. Okay. So this is just a metric to measure uncertainty based on the probabilities of outcomes. Okay. This what it is. It's still not a loss function. I haven't gotten there yet. This is just what Claude Shannon proposed. This is the behavior of the function. This actually is really important too, Because when we create a loss function, and this I want you to really like stop and think about, right? If I create a function like this one, this is the loss function, let's say for some problem, that loss function has, because it's a function, has a graphical representation. Do you see what I'm saying? Obviously. What's important about graphical representations like this one is then you can interpret them almost geometrically. For instance, we can treat this as a mountain, correct? You can imagine that this looks a little bit like a mountain. So what would happen if this was a mountain and a person is standing here? Well, you could argue that that person is fine, just standing there. But what if that person starts to descend? What's going to happen to them eventually? They're going to fall or slide down. Do you see that? So there's this intuition here that we can geometrically say that somebody could slide down. Also, we could say that they're going to slide down. So if let's say the mountain person here goes a little bit to this side, then they'll slide down. Are they going to slide down left or right? As they approach this side, they're going to slide left, right? What if they approach this side? Then they slide right. Do you guys see that? And knowing if you're sliding left or right is really important. Guess what? That's what stochastic gradient descent does through calculus. Calculus has integrals and derivatives, and the derivative essentially takes a function such as this one, which has a graphical representation, and then if I take the derivative of this function at this point in time, I can possibly, through the derivative, figure out that there's a left-leaning tangent. If I take the derivative of a point on this function on this side, then I can figure out a right-leaning tangent. Do you see what I'm saying, guys? And that's the key concept in stochastic gradient descent. So when I said to you guys that when we take the backward and then the step, what is backward doing? Backward takes the function, right? A snapshot of the function at a point in time, and for every one of the weights, imagine that every one of the weights is like a little mountain man moving around. So at that point, it says, okay, the mountain man is here on the function. Guess what? I take the derivative, that's a left-leaning tangent. Or the mountain man is over here. Guess what? That's a right-leaning tangent. And that is what gives me, do I add or subtract? Do you guys remember what I said? So backward gives you that, is it a plus or a minus? And then you do the update. We'll come back to this idea, but this is, right now I'm laying the foundation to say there's a function, there's an equation, this one, you see that, you agree, that gives you a metric. That function given data has a specific shape. And then when we apply the derivative to that function with respect to values at specific points in time, intuitively, the value that we get is equivalent to saying the mountain man is leading to the left or the right. And that's the minus or the plus that we're going to use later in our calculation. Do you see that? So think about that for now. What's different about the approach is that usually the curve is going to be a bowl instead of a mountain. Okay? So but how do I flip that? Just rearrange the function and I will make this into a bowl instead of a mountain. But it's the same principle. I can take the derivative on both. Okay? So anyway, so that's one of the mechanisms of stochastic gradient descent. But let's now go back to just a function of entropy, okay? So I've established we have this function of entropy that deals with probabilities. I run the probabilities from 0 to 1, and the function is telling me the amount of entropy that I have. So here at 0 and at 1, no entropy, no uncertainty. When the value is 0.5 for head, in the binary coin, then we have the highest uncertainty. because it's a fair coin. 50% tail, 50% heads. All right. So, and we summarize the results a little bit so we can see. So the top has the most certainty, actually. So no, it's least certainty. Least certainty, which is uncertainty, right? So it's, yeah. So semantically, least certainty means certainty is most uncertain, right? So yeah. So the top is the most uncertain, highest entropy, least certain, right? So it trips you up a little bit sometimes with the language. So the top has the least amount of certainty because you don't know. You have a 50% chance it's head or tail. At y equals 0, you have the most certainty, right? We've established that in our example, where both sides are head and p head equal 1, then uncertainty is 1. So that's this case. When both sides of the coin are tail and p tail equal 1, then uncertainty is 0, which is these scenarios. Got it? All right. So the entropy is highest when the coin is fair and p head is 0.5. So you can see that there, and you can see that the equation captures that beautifully, as long as you give it the outcomes in terms of probabilities. And for this scenario, we are doing the binary probability case. So now let's look at a couple of examples of calculating entropy. Notice we're still not in cross entropy, we're just in entropy. So we know the equation minus p times logarithm of p. Okay, that's the entropy. So let's do example 1. Calculate the entropy for coin with both sides as head. Okay, so both sides as head. So p head equal 1 and p tail equals 0. So no uncertainty, right? Okay, so notice we have a sum of all the outcomes. So minus 1 times logarithm of 1, that's the first one, plus negative 0 times logarithm of 0, because it's 1 and then 1 minus 1, which is 0. So the entropy is 0. Do you see that? The function captures this beautifully. Now let's try the other example where we have the most uncertainty or the highest entropy. So example 2, entropy of a fair coin so that p head equal 0.5 and p tail equal 0.5 has the highest entropy and maximum uncertainty. And here, just notice in the code, I used log 2 instead of ln, a natural logarithm for the actual computation, but it's the same. So now the sum of the two outcomes, so entropy is equal to negative 0.5 times logarithm of 0.5 plus negative of 0.5 times logarithm of 0.5. Probability head, probability tail. Do you see that, guys? Keep in mind, we use the same probability here and here. And that's going to be the change with cross entropy. So when we compute this, this is going to give us entropy of 1. So yes, when we have this situation, entropy is 1, which means we have the most uncertainty, which ties into this. And when it's certain that one tail is 1, then entropy is 0. Make sense? All right, perfect. So we've established that, those two examples. And here, let's try out computation. Okay, so example 2, probability of 0.5, and you can see it is in fact 1, entropy of 1. Okay, all right, so that's just to corroborate the function as it works. All right, now that you understand entropy, comes cross entropy, which is actually what we use for training classifiers. So imagine this little concept is what makes ChatGPT work, right? So this, our cross entropy. So let's take a look. So cross entropy can be considered a measure of the uncertainty of outcomes due to a mismatch between actual likelihood of outcomes and what we think this likelihood is. Okay, so now what we're going to do is just modify the function so that instead of this being the same probability, we're going to change it to one probability being of the real outcome and one probability being of the predicted outcome. So we have two probability distributions, but that's actually perfectly consistent with a classifier, right? Or a model that we're training. We have the real probability. What is it? The labels. Yeah? The real labels. And then what is the expected one? The model. What the model predicts, right? So the model initially says, I think that's a cat with 0.30, but obviously the model knows it's a cat with 1. So that's the two probabilities. And what we need to do is have a metric that allows that probability of cat to go from 0.3 to 0.98 so that it matches that 1 perfectly. Do you see that? And cross entropy does that beautifully. So let's take a look. So again, the key idea, cross entropy can be considered a measure of the uncertainty of outcomes due to a mismatch between actual likelihood of the outcome, the real labels, and what we think this likelihood is. Okay, so consider if we think a coin is fair, right? We think a coin is fair, but it is not, then we will be surprised by the outcome. Do you guys see that? That's essentially what cross entropy is exploring now. There will be uncertainty about that outcome, and that's what cross entropy measures. If you think the coin is fair, and it is indeed fair, then you will not be surprised. You got what you expected, right? As such, it will have a low entropy. So you see that's the only thing that happened here is we reframe the problem a little bit, and then we have a modification to the equation. So we think of cross entropy as a comparison between two probability distributions. And where do we have two probability distributions? In the classification problem. The labels are one probability distribution that is certainty, and our model is uncertain because it's trying to become certain by learning really well. So we think of cross entropy as a comparison between two probability distributions. The more they match, the lower the cross entropy. Do you see that? And that's exactly what this is doing. If you think the coin is fair and it is indeed fair, then you will not be surprised and you have a low entropy. So the more they match, the lower the cross entropy. And this is exactly what we're optimizing in classification. So that's why we just use this formula. So an exact match is equal to 0 cross entropy. What do we want the losses to be? 0, right? We're minimizing towards 0, so we're minimizing perfectly. Do you have a question? No. Yeah. So an exact match is equal to 0 cross entropy. So in neural networks, the pred output, so in neural networks, the pred outputs are a probability distribution. You know this, right? 0.95, 0.03, 0.02. They add up to 1 thanks to the softmax. They are a probability distribution. And the real outputs are also a probability distribution. 1, 0, 0 adds up to 1, another probability distribution. And we can compare them nicely with this equation. So here's the actual equation. And if you notice, is exactly the same as entropy, except that before this was P and this was P. Now this is the P of Y real and the P of Y pred. That's the difference. So essentially they're the same. So we can compare, right? Because they're both measuring this probability, but just one is of the real data, one is of the predicted. So here's an example to make this more concrete. Let's imagine the case where we want to predict Y real equal 1, right? So Y real is 1, and the model says that Y pred is 0.9, right? So they're close, but not quite there. So if we measure that cross entropy, it's going to be 1, because that's the real, times natural logarithm of 0.9. This is all negative, plus the negative of what? What is the probability? 1. So this is 1 minus 1 times the natural logarithm of 0.1. Do you see that? And we compute this value, and it's going to give us 0.105, 0.10. Okay? Now, let's try the opposite case. What is the, so this model was pretty good, right? You agree that this model, the weights were pretty good. This model over here, notice, it's supposed to predict 1 for that outcome, but what does it predict? 0.1. So you would argue that that model hasn't learned really well. Do you see that? Okay, is that reflected in the cross entropy? We have two cases, right? And at the end of the day, we want weights that produce, remember, we change the weights and the weights predict this 0.9. Do you see that? So, and we compare it to 1 and we measure it as 0.10. We have a set of weights here, another set of weights, and those weights predict 0.1. We want it to be 1, so let's do the computation. Minus 1 times natural logarithm of 0.1, that's this case, minus 0 times logarithm of 0.9, right? The opposites. And notice what happens. This cross entropy is 2.3. So you can see how, because our goal is to minimize cross entropy, what's going to happen? The model is going to start like this, but it's going to do whatever it can during iteration, thanks to stochastic gradient descent, to minimize from 2.3 to 0.10. And as it turns out, when it starts to produce 0.9, it means that it's got a better set of weights that produce an outcome that, when compared, gives you a lower cross entropy. And that's what we optimize. Questions? That's it. That's like the magic. That's the magic of this. Pretty impressive, right? And so that's an entropy and cross entropy. Now let's just once again plot these things a little bit. All right. So if you remember, I have my equation. Now I'm going to change it a little bit, right? Notice that before this was probability and this was probability, but now the same one, but now I'm changing it. It's still the binary case. I'm still in the binary case. Notice it's exactly the same thing, but now I do real logarithm of pred, okay? And then for the binary case, 1 minus real logarithm of 1 minus pred. So the other, if one is heads, the other one is tails. You see that? All right, perfect. So, but it's the same equation, only real and pred. Okay, I'm gonna plot this information. Notice that essentially what happens in a like a binary case where we have 0 or 1 is that one term goes away, right? So if the real is 0, what's going to happen to this term? If real is 0, what happens to that term? 0. And this one is 1 minus 0, so this one stays alive, correct? So this is what gets executed. Now, I said real is 0. What if real is 1? So what happens to this term if real is 1? It stays. Very good. And what happens to this side of the term? 1 minus 1 is 0. So it goes away. Do you guys see that? So essentially, this function actually produces two graphs, because when we have the case of 1, it does this one. And when we have the case of 0, then we have this one over here. Do you see that? Very, very, very cool, right? Very exciting. All right, so let's go ahead and print them. So we have to print them like that, right? So I have to, in this case, I'm going to give real as 1. So I'm going to do that case where this is 1. So this is all 0, and only this determines the function. So if you notice, I do the same thing I did before, and notice what the curve looks like. Do you see that curve? So what's our objective? Because this is in relation to entropy. we're trying to reduce that entropy, right? That's the scenario that was the good one. We are tending towards 1. So what does that tell you? That as this value goes down, you see that here, when it reaches 1, essentially, what's the entropy? 0. Do you see that? You see how the equation does it intuitively, but the graph has this meaning, right? Do you see this? So that's why it's called stochastic gradient descent. What is a gradient? And why the word descent? Do you see? Descent is literally you going down, correct? Gradient just means that the function has this shape, right? So think of it like a little mountain. That's where the name comes from. So the algorithm, cleverly, is called stochastic gradient descent. What does it mean exactly? When you're here at this point, your entropy is really high. Do you see that? But you know that your goal is for it to be 1, right? So when you take the derivative of this function, we'll do this a little bit later, but it's a calculus operation. You take a function, you take a derivative of it at this point in time. What does it tell you? It tells you that this has a tangent to the right. Do you guys see that? That's really important because now you know, oh, it's to the right. That's a plus. So what do? I add my update to my weights. If I keep doing that, I descend down a little bit more. What do I do now? I take the derivative, again, of this function, right? With regards to this point. Gives me a right tangent. What does that mean? Plus. So what do? I take another positive step. If it gave me a negative tangent, what would I do? I would take a step going up. Do you see that? And if I keep taking steps going up, what am I doing effectively? I am increasing the entropy, but that's not the goal. What is the goal? To decrease the entropy. Do you guys see that? That's the whole intuition of this thing. So that's where the name comes from, stochastic gradient descent. The interpretation is that in calculus, graphically, when you do this operation, you get a little line that tells you left or right. And so essentially, you know if you should go up or down. That's it. So eventually, you arrive at 0. Now, this works beautifully because in the binary case, if y is real, 1, it creates that shape. If y was to be 0, we have that scenario here. Remember, this whole thing goes away, and we only look at this side. Well, as it turns out, the curve for this side is a little bit different. Notice that this one goes down like this, right, towards 1. This one goes down in the opposite direction towards 0. So now think of taking you're here, you're the little mountain man here, right? You want your entropy to be low. How do you know if you should go right or left, up or down? Take the derivative of this function, which is nothing more than this function over here, at that point in time for that weight. And guess what? It's going to give you, the previous one gave you a right-leaning tangent. Guess what this one gives you? A left-leaning tangent. So what do? You take a step, not to the right as we were doing, right? Going down. This one descends in the other direction. So when I get if I get here a right, what would I do? I would go up, and that's actually wrong. Do you see that? What I want is for this to tell me left, and then left, left. Do you see that? Now, why do I do that? Because here's another concept. What's the learning rate? The learning rate is equivalent to the size of the step that you're taking here. So for instance, if my learning rate was 8, I would literally say, okay, I'm going right, but boom, I jump over here. That's too crazy of a jump, right? And if my learning rate was 0.00000000003, and I'm going to take a step to the left. Yes, but I barely moved, and I barely moved. And you would run out of iterations before you even get to here. So that's why the learning rate is somewhere like 0.003. Okay. So I'm at this point in time, given all of these terms, take the derivative of it, right, at this position, 0.03. Boom. Take the derivative again, left-leaning tangent, 0.03, boom. Do you see that? And you start taking those little steps, and hopefully you will get to the point where the entropy is minimized and you're at zero. And it just works beautifully. And that's cross entropy. So MSE is even more nicer because it's a bowl, but it's the same idea. It's like an equation that has a graphical representation. When we take the derivative of that function, there's an equivalent interpretation geometrically of this graph that we're getting this line, this tangent that tells you is left or right. Do you guys see that? Does this make sense? We'll come back to this for MSE, but it's a similar idea, okay? So just cross entropy has this shape of these curves like this. I created these curves with Python. I do have them in the PDF in a more, prettier kind of an interpretation, but this is very real. Like this is very real. And so I've done both of them. Okay. All right. So we have about 8 minutes. So now we finished this Jupyter notebook. We're going to go to the notes, right? So again, hopefully you guys are reading these notes because there's some important information there. So let's go to notes, chapter. Wait a minute. Is it 4? Yeah, 4. I think it's 4. Okay, so what I just said, I mean, everything I've been saying is this, because this is what we discussed last week, but we're going to go. Yeah, and so this is entropy cross entropy. So we discussed that. This is binary cross entropy. This is just those same equations summarized. Some people will express these as two separate functions, but I've shown you that you can actually write them as a single function, which is what's here, right? And if you look at this carefully, y times log of h and y minus 1 log of 1 minus h is exactly what I wrote in the code. So it's and because of the 0 and 1 of the terms cancels out. Okay. So essentially everything that I just said, but here are the graphs a little bit more, more curvy. You see that, guys? So that's the binary case. When I say the binary case, I literally mean cat or dog. Up or down, a binary problem. But not all of your classification problems are binary, right? What about Iris? That has 3 classes. What about MNIST? That has 10 classes. So that's going to be called the multi-class cross entropy, all right? Which is this one over here, but it's actually not that complex to understand. Pretty much the same thing. So let's take a look. So the following code shows the implementation of the multi-class loss function for anything. I just said here for logistic regression, as if we were writing out the equation. So that's true. Like you've seen me write the equations. Obviously, we've been using in our PyTorch examples the function built in by PyTorch. I do recommend that you use the function that PyTorch uses, but you can also just write it out with the equations. So here, one important thing to mention is that I have noticed that this model does not always converge. When you write out the equations to correct this, you use tricks like clipping and things like that. So to avoid not a number, which can happen. This approach of writing out the cost functions or equations is not always the most optimal, but I have shown it here for contrast between linear regression and logistic regression. A better approach is to use the PyTorch built-in functions of cross entropy, which provide a lot more. So for instance, if you use the equations, obviously you have to do the one-hot encoding, right? It's not going to do it for you. All right, so let's take a look at the example of multi-class cross entropy. So the following statement is where we invoke the multi-class cross entropy loss function. And that's literally it. Now, this might look different to the equation I gave you because there was a sum. Remember, there was a sum and all that, an idea of iteration. But remember that this is tensor operations. So the data is provided as a tensor. Do you see that? So we're actually going to give it not a list of probabilities, but actually a vector of the probabilities. So we can operate at the vector level. Do you guys get that? So that's the key intuition. So an easy way to understand the multi-class cross entropy loss function is with an example. Assume we try to classify images of vehicles and we have 5 categories for plane, car, boat, bike, balloon, right? We have 5 classes. Given a cross entropy model, we have the following output vector for this multi-class problem. So this is the predicted vector of the neural network, right? Do you guys remember? 0.3, 0.2, 0.05, 0.05, and 0.40. So this is 0.5. Yeah, it adds up to 1. So it's the probability distribution over the 5 classes that the model. So if this has gone through the softmax, this is what you get. Got it? That's the model. According to this model, the image is 30% plane, 20% car, 5% boat, 5% bike, and 40% balloon. The model is not very confident about what type of vehicle it is. In contrast, the label for each image would tell us with great certainty. So the label would be 1,0000. It knows for sure then that this is what? A plane. Very good. That's the label, the annotation. So that is a plane. We can calculate the cross entropy to measure our model's cost. Exactly what we do, right? So the probability of P and log, the probability of P times the probability of P times the log of the probability of Q. Got it? The real versus P is the real, P times logarithm of Q, the predicted. Do you guys see it's exactly the same thing, only non-binary, now multi-outcome. So we calculate these probabilities. Now notice here it says sum, but it's actually a vector operation. So, all right, so if we calculate the values of this vector, we get essentially 1 times log of 0.3 plus 0 times log of 0.2 and so on. And that calculation gives us a cross entropy of 1.2. Do you see that? 1.2. Now, after training, the model is much better, right? And it can predict the following, 0.90. Notice how before it predicted like 0.3, 0.2, 0.40. Now it predicts 0.98, 0.01. So obviously this model is much better. These probabilities add up to 1. Do you guys see that? All right. So we do the same thing again, right? Because we're in fact doing this all the time, right? Every iteration, we do this calculation and we use those values to back propagate to update the weights. But at this point, we've completed that process. We know that the weights are very good. So now we compute the cross entropy just like we did over here. 1 times log of 0.98, 0 times log of 0.1, 0 times log of 0.1, 0 log 0, 0 log 0. When we calculate this cross entropy, it is 0.02. Our goal when we are optimizing cross entropy is to do what? For it to go down, right? We want our loss to go down. So in which scenario did we get the lower cross entropy? In the scenario where we had a lot of uncertainty in the prediction model versus the real, or in the scenario where we had good certainty that compared to the real data? The second one, right? So here you can see the loss started at 1.20, which is usually what you guys have seen, right? And then it started to go down, and it finally starts to plateau at 0.02. We are optimizing cross entropy to reduce that loss. Therefore, with the cross entropy loss, you compare predicted values to labels. As the prediction improves, the cross entropy value goes down. That's it. All right, so that is cross entropy. Are there any questions? Does it make sense? This is the loss that trains ChatGPT, iris classification, most classification problems. MNIST, Cipher10, you name it. Okay. Yeah, so that's it. So that concludes, one of our first introductions to the stochastic gradient descent, the training side, right? So today we looked at loss cross entropy as the loss. Later we'll touch on MSE a little bit more similar ideas. And as we move forward, we're going to look at some examples of actually the derivatives and how that works. Remember, the graphical thing is something humans invent, right? That's a human thing. The fact that these curves in my mind, gradients, little men going down, that's just our minds are creating that. The computer doesn't create a plot and look at it. And computer has a function, takes a derivative, and there's going to be a value which is positive or negative, and it goes from there. Okay, but both cases are true. They're correlated, right? And the name comes from that, stochastic gradient descent. Okay. All right. So I will end this here.